We, humans, love fireworks. We spend billions of dollars every year to watch them. So it seems fitting that one of the most popular theories for how the universe might end involves a Big Bang, an unimaginably powerful explosion that obliterates everything. But what if the heat death of the universe is less Independence Day and more Blue Monday? What if instead of going out in a blaze of glory, the universe ends quietly, not with a bang, but with a whimper? Will the last 100 billion years of the universe be spent in silence? That's what we'll explore today. In a recent paper, researchers put their own spin on the heat death of the universe, giving us yet another reason to despair about our fate. Their simulation suggests that at the very end, everything would vanish into nothing. And maybe this isn't so surprising. I mean, where do you expect the universe to go after it dies? You can't fit infinite into finite. Or maybe you can, but it doesn't really make sense. How can everything continue existing when there's nowhere for it to exist in? The heat death of the universe is by definition the end of the universe. It sounds simple, but it's actually a surprisingly complex problem. For example, what happens to the particles that make up black holes? Do they cease to exist? What happens to dark energy? Does it even exist? Or does it just keep expanding the universe until it tears itself apart? And then there's the question of what happens to all the light in the universe. Light travels through space at 299,792,458 meters per second. If the universe keeps expanding, it means light has to travel further and further to reach its destination. And eventually, it just won't make it. As the universe expands, the average distance between any two random points increases exponentially. Eventually, this means that light from distant stars no longer reaches us. This is known as the horizon problem in cosmology. As the universe gets bigger, it becomes harder and harder for light to cross the vast distances between objects. When all communication breaks down, those objects become causally disconnected from each other, meaning that there's no way for them to influence each other. In other words, the universe splits into isolated regions that each evolve independently. If you remember high school physics, you might recall something called conservation of entropy. Entropy is basically a measure of disorder. For example, a nice warm cup of tea left out in the open will eventually cool down, because there are many more ways for the tea to be cold than hot. There are 10 million trillion ways for it to be cold, whereas there's only one way for it to be exactly at the temperature you poured it at. There are far fewer ways for your bedroom to be tidy than messy. Your bed is made, your clothes are put away, and your shoes are neatly lined up by the door. But leave your room alone for a few days, and it'll soon be a disaster zone. Again, there are simply far more ways for things to be messy than tidy. So, entropy says that things tend to move from order to disorder. Why? Because there are vastly more ways for things to be disordered than ordered. A highly ordered system is a low entropy state. And when entropy wins out, you get a state of maximum disorder. The death of the universe is therefore a maximum entropy state. Once everything is evenly distributed, there's nowhere for it to go but down. No more stars will form. The ones that are still shining will slowly burn out one by one, until every single one goes out and every galaxy fades to darkness. All of the matter in the universe will eventually turn into a black hole soup. Black holes will continue to evaporate via Hawking radiation until they too disappear. The only thing left will be a vast, cold, dark, and empty expanse. The universe ends in silence. Not exactly a satisfying ending. But wait! Let's step back! All of these scenarios depend on the idea that the laws of nature continue to function as they do today. They assume that gravity and electromagnetism work the same way, and that nuclear fusion and fission behave as they do on Earth. But we have no idea if that'll actually happen. Physicists have long wondered whether the fundamental constants of nature could change over time. They could vary from place to place. For example, if you were inside a black hole, the laws of physics would seem to break down at the singularity. So maybe at the end of the universe, we can't use the current laws of physics to tell what will happen. Maybe they change. It's also possible that the universe doesn't end at all. Physicists aren't sure if the Big Bang was really the beginning. Many of them think that time began around 100 billion years before the Big Bang. And they don't know where that time came from. Did the universe begin in a previous heat death? Are we living in a never-ending cycle of birth, life, and death? These questions aren't easy to answer, and we don't know how to test them. But it's possible that the heat death of the universe doesn't really exist. The authors of the recent paper, however, assumed that the laws of physics would stay constant and worked within that framework. Now, what they did was run computer simulations of several models of the universe. One was a simplified model of our universe. Another contained no dark energy, while a third had no dark matter. They found that regardless of the model, they all seemed to converge to the same heat death scenario. The team first simulated a universe that looked much like our own. In this simulation, the amount of matter, dark energy, and dark matter stayed the same. The result was a universe that expanded faster and faster, breaking apart into smaller and smaller chunks. Then they turned off dark energy, which in our universe makes up roughly 68% of all energy. The result was the same, without dark energy. The expansion of the universe slowed, and the galaxies were torn apart by the gravitational drag of the black holes. Again, the result was a bunch of tiny universes that eventually faded into darkness. Finally, they removed dark matter, which makes up roughly 27% of all matter in the universe. Without dark matter, gravity wins out, and the universe collapses in on itself. The result is a huge black hole surrounded by a bunch of smaller ones. Again, the outcome is the same: total darkness. So we have to conclude that the heat death of the universe is pretty robust. Whether or not dark energy exists or dark matter, it doesn't really matter. The universe will still expand, everything will drift apart, and darkness will fall. The one variable that they could unchange without changing the fundamental laws of physics was the speed of light. If that changed, then the heat death would look different. But they didn't want to change the laws of physics. So they kept the speed of light constant and stuck with the original heat death scenario. Okay, but what if the heat death doesn't happen? What if the universe doesn't end at all? Well, even then, it wouldn't be much fun to live there. Take our hypothetical universe without dark energy. In that case, the expansion of the universe slows down and we re-left in the dark as the nearby galaxies drift away from us. But we wouldn't be totally alone. We'd still be able to see other stars in our galaxy. And as long as the sun keeps shining, life would be pretty sweet. But what about the hypothetical universe without dark matter? Without dark matter, gravity wins out and the universe collapses in on itself. Our solar system would probably survive intact because it's fairly small compared to most other star systems. But eventually, the inevitable heat death would occur anyway. Even if the heat death didn't happen, there'd still be no new stars forming. The metal-enriched gas clouds necessary to produce new stars would have already formed all the planets and brown dwarfs. So there'd be nothing left to make new stars. So the future looks bleak. We may be living through the universe's golden age right now, but it won't last forever. Either way, we're doomed. It might be fun to speculate about what will happen, but it's better to focus on what we can control. And speaking of what you can control, you can subscribe for more videos about the amazing discoveries and mysteries of our universe. Thanks for watching. See you next time!